Nenomatica, where mathematics meets YouTube excellence. Welcome to our mathematics lesson. Today, we're going to solve a challenging inequality proof step by step. Let's begin. Let's look at our example. We need to prove the inequality x to the power of 5 plus y to the power of 5 is greater than or equal to x cubed y squared plus y cubed x squared, given that x is less than or equal to y. Let's start by rearranging the inequality to group similar terms. We move all terms to one side of the inequality. We get x to the power of 5 minus x cubed y squared plus y to the power of 5 minus y cubed x squared is greater than or equal to 0. Next, we'll factor out common terms from each group. From the first group, we can factor out x cubed, giving us x cubed times x squared minus y squared. From the second group, we can factor out y cubed, giving us y cubed times y squared minus x squared. We notice that both terms have a common factor of x squared minus y squared. We can factor this out to get x squared minus y squared times x cubed minus y cubed is greater than or equal to 0. Now, let's consider our condition that x is less than or equal to y. Given that x is less than or equal to y, we can deduce two important facts. First, x squared minus y squared is less than or equal to 0, because when x is less than or equal to y, squaring both sides preserves the inequality. Second, x cubed minus y cubed is also less than or equal to 0 for the same reason, but with cubes. When we multiply two negative numbers, we get a positive result. Since both x squared minus y squared and x cubed minus y cubed are less than or equal to 0 based on our condition, their product is greater than or equal to 0. Therefore, we've proven that the original inequality, x to the power of 5 plus y to the power of 5 is greater than or equal to x cubed y squared plus y cubed x squared, is true when x is less than or equal to y. To summarize what we've learned, first, we rearranged the terms to group similar expressions. Then we factored out common terms to simplify the expression. Next, we analyzed the implications of our condition, x less than or equal to y. Finally, we applied the sign rule to prove the inequality. This proof demonstrates important techniques in algebra, including factoring, analyzing inequalities, and applying sign rules. We need to prove the following inequality: 1 over 2 times 3 over 4 times 5 over 6 times, and so on until 2n minus 1 over 2n is less than 1 over square root of 2n plus 1. To solve this problem, we'll use a key property of fractions. Given positive numbers, a, b, and k, if a over b is less than a plus k over b plus k, then we can apply this rule to our problem. Let's begin by taking k equal to 1 in our fraction property. This gives us the following relationship. 1 over 2 is less than 1 plus 1 over 2 plus 1, which simplifies to 1 over 2 is less than 2 over 3. Next, we can apply the same property to the fraction 3 over 4. We get 3 over 4 is less than 3 plus 1 over 4 plus 1, which simplifies to 3 over 4 is less than 4 over 5. Following the same pattern, we apply our property to 5 over 6. We get 5 over 6 is less than 5 plus 1 over 6 plus 1, which simplifies to 5 over 6 is less than 6 over 7. Following this pattern, we can apply our property to the last fraction, 2n minus 1 over 2n. We get 2n minus 1 over 2n is less than 2n minus 1 plus 1 over 2n plus 1, which simplifies to 2n minus 1 over 2n is less than 2n over 2n plus 1. Now we can multiply all these inequalities together. On the left side, we get our original expression, 1 over 2 times 3 over 4 times 5 over 6, and so on until 2n minus 1 over 2n. On the right side, we get 2 over 3 times 4 over 5 times 6 over 7, and so on until 2n over 2n plus 1. Let's expand these products. The left side remains as 1 over 2 times 3 over 4 times 5 over 6, and so on. For the right side, we can rewrite it as 2 times 4 times 6, and so on until 2n divided by 3 times 5 times 7, and so on until 2n plus 1. Now, this inequality involves products of odd numbers in the numerator and products of even numbers in the denominator. Let's start by observing the left side of the inequality. We have the product of two fractions, both having the same form. We can simplify this product as the square of this fraction. Let's focus on the right side of our original inequality. We can apply the rule of fraction multiplication. The right side shows the product of different fractions. Now, let's rearrange the right side of the inequality to see if we can simplify it further. When we multiply these two fractions, we get this expression. We can apply the cancellation property to simplify our expression. Notice that the denominator contains a common factor of 2 times 4 times 6, and so on up to 2n, which appears both in the numerator and denominator. These terms cancel out. Now, we can restate our inequality using the simplified expressions. On the left side, we have the square of our fraction, and on the right side, we have the simplified product. Based on the inequality properties, we can further simplify our expression. According to the image, the next step leads us to this inequality. Now we can apply the square root property of inequalities. Since both sides of the inequality are positive, taking the square root preserves the inequality direction. We can simplify the square root on the right. This leads us to our final inequality as shown in the algorithm. Finally, we can expand the fraction into its component terms. This gives us this expanded form of our inequality, which completes our proof. Let's summarize what we've accomplished in this proof. We started with a complex inequality involving products of odd and even numbers. We simplified both sides step by step, applied various algebraic rules, and eventually arrived at our final result. This technique of systematic transformation is powerful for proving complex inequalities. Let's start with our example. We need to prove the following inequality. A times b times the quantity a plus b plus a times c times the quantity a plus c plus b times c times the quantity b plus c is greater than or equal to 6 times a times b times c, where a, b, and c are all positive real numbers. Let's solve this step by step. First, since a, b, and c are all positive, we can divide both sides of the inequality by abc. Next, we'll simplify each fraction. For the first term, 8b times a plus b divided by abc simplifies to a plus b divided by c. For the second term, we get a plus c divided by b. And for the third term, we get b plus c divided by a. On the right side, 6abc divided by abc just equals 6. Let's rewrite our expression using parentheses to group terms. We'll rewrite a plus b over c as a over c plus b over c. Similarly, we'll rewrite the other fractions with the same approach. Now, let's rearrange these terms to group them differently. We'll group the a over b with b over a, the a over c with c over a, and the b over c with c over b. Here comes the key insight. For any two positive numbers, their arithmetic mean is always greater than or equal to their harmonic mean. In algebraic terms, for positive numbers x and y, the sum of x over y plus y over x is always greater than or equal to 2. This is a special case of the AMHM inequality. We can apply this to each of our 3 group terms. Now, we can substitute these inequalities into our expression. We have that a over b plus b over is greater than or equal to 2, over c plus c over is greater than or equal to 2, and b over c plus c over b is also greater than or equal to 2. So our expression becomes 2 plus 2 plus 2, which is 6. Finally, we simplify to get 6 is greater than or equal to 6, which is always true. Since we've shown that our expression is always greater than or equal to 6, we've proven the original inequality. Therefore, we've proven that ab times the quantity a plus b plus ac times the quantity a plus c plus bc times the quantity b plus c is greater than or equal to 6 times abc when ab and c are positive. The key insight was using the AMHM inequality for each pair of terms. The inequality we want to prove is a 1 plus a 2 plus an is less than or equal to the square root of n times the sum of a 1 squared plus an squared. Before diving into the proof, let's understand what this inequality means. It essentially tells us that the square of the sum of numbers is bounded by the product of the number of terms and the sum of their squares. This is a fundamental result with applications in various fields of mathematics. To prove this inequality, we'll use the general form of the Cauchy-Schwarz inequality, which is the square of the dot product of two vectors is less than or equal to the product of the sums of their squares. In our case, we'll choose vectors intelligently to derive our target inequality. The first step in our proof is to make a clever substitution. Let's set b1 equals b2 equals bn equals 1. With this substitution, we get the equation. If b1 equals b2 equals bn equals 1, then the left side of the Cauchy-Schwarz inequality becomes the square of a 1 plus a 2 plus an. For the right side, we have the sum of a 1 squared plus an squared multiplied by the sum of 1n times, which is just n. So our inequality becomes the square of a 1 plus an is less than or equal to the sum of squares times n. Finally, we take the square root of both sides. Since we're dealing with non-negative values, taking the square root preserves the inequality, and we get our original inequality that we wanted to prove. A 1 plus a 2 plus an is less than or equal to the square root of n times the sum of a 1 squared plus an squared. Let's summarize what we've learned. We proved the Cauchy-Schwarz inequality by 1. Starting with the general form of the Cauchy-Schwarz inequality 2. Setting b1 equals b2 equals bn equals 1, 3. Simplifying both sides of the inequality 4. Taking the square root of both sides to get our target result. This inequality is extremely useful in many areas of mathematics, including geometry, analysis, probability theory, and even in applications like signal processing. Welcome to our math video. Today, we're going to solve an interesting inequality problem using the Cauchy-Schwarz inequality. Let's dive into the problem. Here is our problem. We need to prove that the following inequality is true. A over b plus c over c plus a plus c over a plus b is greater than or equal to 3 over 2, where a, b, and c are all positive real numbers. To solve this problem, we'll use a powerful inequality in mathematics called the Cauchy-Schwarz inequality. The inequality states that for any positive numbers, a 1 through n, when we multiply the sum of these numbers by the sum of their reciprocals, the result is greater than or equal to n squared, where n is the number of terms. This can be written mathematically as the sum of a1 through n multiplied by the sum of 1 over a1 through 1 over n is greater than or equal to n squared. This is the key result we'll use to solve our problem. Let's start applying this inequality to our problem. First, we notice that we can rewrite the terms in our inequality using the same variables. So we look at the expressions a plus b, b plus c, and c plus a. We can see that these three sums form a pattern that matches the structure of the Cauchy-Schwarz inequality, where we have a plus b plus c on the left and the sum of their reciprocals on the right. Now, let's simplify the left terms in our equation. We a va plus b plus c plus a. If we collect like terms, we get 2a plus 2b plus 2c, which simplifies to 2 times a plus b plus c. We can further simplify this expression. Let's divide both sides by 2. On the left, we get a plus b plus c multiplied by the sum of the reciprocal terms. On the right, we get 9 divided by 2. Now, let's rearrange to get closer to our original problem. We'll distribute a plus b plus c to each term in the brackets. This gives us a plus b plus c over a plus b, plus a plus b plus c over b plus c, plus a plus b plus c over c plus a, which is greater than or equal to 9 over 2. Let's break down each of these fractions into simpler parts. For example, the term a plus b plus c over a plus b can be rewritten as a plus b over a plus b plus c over a plus b, which is equal to 1 plus c over a plus b. Similarly, we can break down the other terms. This gives us 1 plus c over a plus b, plus 1 plus a over b plus c, plus 1 plus b over c plus a, which is greater than or equal to 9 over 2. Now let's combine like terms. The 1's sum to 3, so we get 3 plus c over a plus b plus a over b plus c plus b over c plus a is greater than or equal to 9 over 2. Subtracting 3 from both sides, we get c over a plus b plus a over b plus c plus b over c plus a is greater than or equal to 9 over 2 minus 3, which is equal to 3 over 2. And there we have it. We've proven that a over b plus c plus b over c plus a plus c over a plus b is greater than or equal to 3 over 2, which was what we wanted to prove. This proof demonstrates the power of the Cauchy-Schwarz inequality in solving complex inequality problems. To summarize what we've learned, first, we recognized that we could apply the Cauchy-Schwarz inequality to our problem. Second, we identified the right terms to use in the inequality, a plus b, b plus c, and c plus a. Third, we performed algebraic manipulations to transform the inequality into the form we needed. And finally, we proved that the given inequality is indeed true. This approach demonstrates how powerful inequalities like the Cauchy-Schwarz inequality can be used to solve seemingly complex problems. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.